So I changed my mind. I decided that everyone should go watch the podcast, and the reason is because I've tried to explain WF Algebra in videos, and I cannot explain it in a way that's more clear than the way I explained it in the podcast. And also with the podcast, there's Craig sitting there asking me questions. So basically we went over this. It was a different document, but we went over... I took that document and edited it a bit, and that's Revelations 14. Link will be in the description. And so we basically, I don't think I've added anything to this. So there's maybe more I want to talk about, so maybe clarify what exactly a proof means in WF Algebra, clarify some things. But instead, for now, what I'm going to focus on is the changes I have made since that podcast. So there's almost no changes to this document. So first we talk about the traditional primitives of Boolean algebra. So traditionally in Boolean algebra, you think about things. These are sort of the three operations of set theory. Again, I mentioned mathematicians think of Boolean algebra as just the thing below set theory. So sets are a functor over Boolean algebra, if you prefer category theory. We have the union, the intersection, and the complement. So instead, we use symmetric difference, because that ends up being the theory ends up being a lot cleaner, and we can use very straightforward algebraic notation in Z mod 2 in order to do that. And this is why XOR is a better primitive, because the three basic primitives correspond to normal arithmetic mod 2, XOR is plus, AND is AB. I explained in a previous video what mod 2 arithmetic is, and L naught is 1 plus A. This is the standard notation for equals in modular arithmetic. Right. So, the idea is you can take the tools from modular arithmetic and port them into talking about logic. And the way you can tell that these sort of two systems are equivalent is because you can write exclusive OR as a combination of I OR, and not. So exclusive OR is, so XOR AB is equal to I OR AB and not AND AB. So there, you can write it in terms of these three. So therefore any expression you can write in one, you can write in the other. And likewise, first example is, how do you write inclusive OR in the WF algebra primitives? So we know, I just outlined very briefly, how do you write exclusive OR in the Boolean algebra primitives, and then this first example, that we're going to get to in a minute, is how do you write IOR in the WF algebra primitives. And so if you can write one in terms of the other, they're equivalent. Right, they're like languages that you can translate between exactly. There's very few, I don't think there's any examples of natural languages where you can translate perfectly from one to the other, but in math those are very common. Anyway, so yeah, we can port all the tools we have for modular arithmetic into talking about logic. So that's what we're going to be doing in this revelation. So Wildberger, his innovation was, this may not be 100% true. So this is like 90% true. All truth tables correspond uniquely to a specific polynomial in Z mod 2. Wildberger calls polynomials polynumbers, and in my algebra series I'm going to talk about polynumbers and why they're a better idea, because it's a data structure rather than... Wildberger has sort of intrinsic allergy to poorly defined concepts like variables, and instead he prefers data structures. A polynumber is a data structure, and it's kind of harder to pin down what a polynomial is. Anyway, he calls these Bool polynumbers. I'm calling these WF polynumbers in this document. In WFC, they're called sentences. Okay, and I'm going to, if you looked at the code, if you watched the podcast, it's very clear why the sentence terminology makes sense. So, and when we get to examples, I'll explain what that means. Yeah, WF polynumbers have a canonical reduction procedure. So you can always take a bunch of sentences combined in any way and reduce it down to a single sentence. Unique representation in canonical form, sum of products, that means a sentence, and I'll get to what that means. And Boolean functions written using the Boolean algebra primitives do not, and it's analogous to this type of problem. So this is old QAnal code. plus of 1/10 and 2/10 is equal to 3/10. In QAnal, that's true. And with floats, 0.1 plus 0.2 is equal to 0.3. That's false. Now, what it means is, with Boolean algebra, you have some representation ambiguity where it's not clear what the right way to write something is, and if you write two expressions, it's not obvious how to prove that whether or not they're the same expression. And in WF algebra, you can reduce both of them to a canonical form, at which point you just look at them and they're either equal or they're not. Right. So in order to check if two Boolean functions written using the Boolean algebra primitives are equal, you either have to prove that they are equal algebraically using the identities of Boolean algebra, not easy or even possible in general, or check both functions against every input. Right, one of your homework problems, I don't know if I included the homework problems. I might need to delete that. In order to check if two reduced WF polynumbers are equal, you just look at them and they're either equal or they aren't. Meaning in Erlang terms, WF polynumbers are amenable to pattern matching and Boolean functions are not. And remember, every computable function corresponds uniquely to a specific set of one or more WF polynumbers. You get more than one polynumber. I was going to do a revelation where I do a binary adder and write it as WF polynumbers. Because WF, Wildberger's original orientation was towards circuits. And I want to maybe circle back to that orientation. I also have not talked about the Boole-Mobius transform and maybe want to talk about that in this playlist. I got to work more on QAnal in order for that to work. We'll see. But you get more than one polynumber if you have more than one binary output variable. So for instance, in an 8-bit binary adder, you'd have, 8-digit binary numbers. You'd have 8 WF polynumbers, one for each digit in the output. 16 input variables, one for each digit in the two inputs. Right, and there's a caveat, which is that you have size of the universe problems. And Wildberger talked about this in one of his videos. But that also exists within Boolean algebra, so the fact that we've made it cleaner is an improvement. So here, we're going to go through examples and then maybe define things in the later chapter. So, yeah, this will build intuition such that the formal definitions make sense. So the truth table for inclusive OR, right, we have inclusive OR, yeah, it's inclusive OR. And I'm going to abuse the case, right, this is what I explained, I think, in the second video. Abuse the term positive case to mean the cases of the function where the value of the function is 1. Negative cases are where it's 0. So you pick the positive cases, you write the indicator. See, the problem with all of these botched takes is I can't remember what I covered and what I haven't, because I remember talking about this like 50 times, and I don't remember whether it ever made it onto a video that I actually published. So maybe I should go over this. You know what? Go watch the podcast because I explain this. So you write the indicator for the row. This is the expression that evaluates to 1 on that specific pattern of inputs and 0 for every other input. Right, and it's easy to cook up these indicators. Once you see a couple examples, it's obvious why it works. So the expression 1 plus a times b evaluates to 1 when a is equal to 0 and b is equal to 1, and otherwise will evaluate to 0. Because if you put like a equals 0, this will be 0. And if b is equal to 0, this will be 0. And so you take the product of two things. Then you take the XOR or mod 2 sum of the indicators. You then have a sum of algebraic expressions. 1 corresponds to each positive case of the function. Each summand will be 1 when it matches its pattern of arguments and will otherwise be 0. Therefore, the total expression will be 1 whenever the function is 1 and will otherwise be 0 just as the function is. Therefore, the algebraic expression matches the function. This is equivalent to taking a sum over all inputs of indicator times value, because the value on the negative cases is 0, so therefore the terms in the sum disappear. Right, so you write it out as blah plus blah plus blah plus blah. This is the mod 2 sum of the indicators. Well, if none of the indicators are true, all of those indicators will be 0, so you have a sum of a bunch of things which is 0. So that'll happen on the cases where the value of the function is 0. You know what, let's just get to an example. Okay. Right, the algebraic expression matches the function. We'll see some examples. This is equivalent of taking a sum over all inputs of indicator times value, because the value on the negative cases is 0. So therefore the terms in the sum disappear. So this reasoning pattern of multiplying the value of a function by the indicator function over some subset of its domain, then taking the sum, is the core reasoning pattern of measure theory. Right, and reduce the expression into a sentence or sum of products form. it's a sentence or WF polynumber of the Boolean function. So here is a list of all of the connectives. And by connectives, what I mean is, this is just a common thing you need to do in math. Here, I wanted to actually find some examples. Let me find a textbook. Let's see. What do I have? Trying to find a Rudin book because he has a lot of theorems that are written like this. Where are my Rudin books? Okay. Here's an algebra. I can't find where my Rudin book went. Algebra or algebraic topology might be good examples. Okay. Here's Algebra by Artin. I also have an algebraic topology book. So let me find a theorem. Okay. See. Trying to find a theorem that's relatively easy to understand. This is going to take too long. Rudin is really the best guy for this. Let me look in the algebraic topology book real briefly, and then I'll give up. Okay. Okay, so this is let me where's, do I have the drawing pad? Yeah, I do. This is a good theorem. So this is in, go away. Shit. I need to clean my desk. Okay. Get all this shit off my desk. Okay, this is a good example. Sorry, you can't see it. Okay. You're not going to understand any of these terms, but what's important is to see how everything connects together. So this is Lectures on Algebraic Topology by Greenberg. Is it with a U or an E? E. Algebraic topology has a lot of really like clearly stated theorems, if that makes their theory here. You'll see from this example. So this is Theorem 6.11, page 25. It says if, let me write it. If X is a topological group, then for any covering space never mind what this notation means, and a point E naught in the, okay, and a point E naught it's just and point E naught in the fiber of the neutral element. He spells fiber wrong because he's British. little x naught, there is a unique structure of topological group E. E for which, oh my god, for which E naught the neutral element in P is a homomorphism. Not ediment, oh well, element. And P is a homomorphism. There's so much logic in this, well, paragraph basically. Okay, so my point, what I wanted to highlight, is the logic, is the way that you connect things. So X is a topological group. So is a topological group means there are certain things that are true about X. If then for any covering, so if something is a covering space, then if something is a covering space with a point E naught, and E naught has to have the property that it's in the fiber of the neutral element X0, then there is a structure of topological group on E, and it's unique, which means that if you find one of the structures, that's the only one. Topological group on E, you have to prove it's a topological group. And then it also has this property for which E naught is the neutral element and P is a homomorphism. So there's a lot of structure here, but there's some very primitive building blocks on which everything else is based. Right? So it's if then, and, XOR, and my point with all of this is you can write, if you do it right, you can write everything as a truth table. You can write everything, and it's not necessarily one of these truth tables because I didn't write every possible truth table out. And one thing I want to do in the Lisp server is allow you to have like variables and input arbitrary truth tables, but I haven't done that yet. Logical relative complement, yeah. Inclusive or, implied by, IFF. And the point is that these are like common ways of constructing larger logical statements out of smaller ones. And this is just one. I mean, you can see how much information density there is in literally a sentence in this book. And this book is hundreds of pages long. And there's so much information just in this one sentence. But it's so specific too. If X is a what's a topological group? Oh boy, that's a lot of talking about. Groups are simple to understand relatively. Topology is a giant mess because it doesn't actually. The CIA invented topology. Let's just leave it at that. So, inclusive or. Right. So here's our verbose example. So we write down what the positive cases are and their indicators, and you should be able to see pretty clearly how you construct these indicators. If it's 0, you do 1 plus, and if it's 1, you just leave it, and then you take the product of the two. Okay? Let's go to water. All right, and we take the sum of the indicators, which are the things on the right side of the arrow, and get the expression. Now the point is that exactly either 0 of these so either none of these terms in the sum will be 1, or exactly one of them will be. You will never have the case where more than one of these terms is equal to 1 when you write it like this as a sum of indicators. Therefore, this sum of indicators matches up here. Does that make sense? I hope it makes sense. Because if it's 0, we could have written 0 times the indicator for this row, in which case then you would take that indicator and multiply it by 0, and so it's pointless to write it down. And then what we're doing is something that kind of seems counterintuitive from this perspective, which is reducing it by applying the distributive law. So apply the distributive law in the first term, so this 1 plus a times b becomes b plus ab. This a times 1 plus b becomes a plus ab, and then we have an ab over here. Anything plus itself is equal to 0 mod 2, so ab plus ab. The two of these cancel out, and then you get b plus ab, but addition is commutative in the integers. So the WF Pauli number for inclusive OR is logical inclusive OR of AB is A plus B plus AB, and let's just check that this works for each of our cases. Okay. 0 to 0, right. So we haven't changed any of the values here. So if this works, which I think the logic is clear why that works, then this will work too, but let's just check by hand. 0, 0 maps to 0. Well, A is equal to 0, B is equal to 0, so 0 plus 0 plus 0 times 0 is 0. Okay, 0, 1. 0 plus 1 plus 0 times 1 is 1. 1 and 0. 1 plus 0 plus 0 plus 1 times 0 is 1. And then this one is where you get the canceling. So this you get 1 plus 1 plus 1 times 1, which is 1. Because it's 3, which is 1 in 2-hour clock arithmetic. Okay. So then there's this other thing you can do, which is, you know what, go watch the podcast if you want to understand this. Craig called this G-ing it, and I think that's actually a good way. But basically you just take 1 plus exclusive OR, take the compute the Pauli number for that, and note that'll probably be easier because there would only be one positive case if you take the not of inclusive OR. And then once you find the Pauli number for that, you add 1 to that, and then you would get the Pauli number for inclusive OR back. So this is an example. Maybe pause the video and look at this if you don't believe me. Yeah. So more examples. I'm going to let you read the document. It's pretty obvious once you see it how to do this. And then in the code, these are hard-coded in, but there's no reason you can't write code that just enumerates all of the possible cases of a function and figures this out. In fact, the earliest version of WFC actually did that, and then when I was in a hurry, I rewrote it so it didn't do that. But I do want to go back and have it do it properly, and that way you can input arbitrary truth tables more easily. But let's talk about how to convert logical connectives to WF Pauli numbers. Yeah, so, right, so there are two problems here, and this section contains a general outline regarding how to solve them. So given a truth table, find its Pauli number, given a Pauli number, find its truth table. The second problem is very trivial because you just plug values in, right? So here, let's, I meant to remind you, telnet, orange pill, 2360, I need to put my website back up. Because I was using GitLab Pages, and then it was doing some nonsense with the DNS, and so I couldn't put this up. I couldn't get the domain to work for this, and then so I took down my website, and I'm gonna put it back up on this server, but I haven't gotten around to that. And then I also got to figure out how to do HTTPS. I got to figure out Let's Encrypt, and that's like a day of work. Anyway. So let's do LIOR AB. Oh, it's IOR AB. There we go. So this is A plus B plus AB, but it's written as S expression. So the way this works, these things inside, these atoms, these are called WF characters. the products are called words and the sums are called sentences. That's the terminology. Okay. And if you watch the podcast, you would know that. Okay. But all you have to do, oops, I don't have readline. I want to add that. You just enumerate the cases of the function. And I also want to let you do multi-line input. And all you have to do is just automate enumerating the cases of the function, and then you can reassemble the truth table. That's not difficult. And so I want to be able to pretty print a truth table. The first problem, there's two-ish approaches, which is Bool reduction. So either Bool reduction, so basically a compiler, you write a syntax tree for the algebraic expressions, and then a rule that reduces it to a sum of products. That's the way that WFC works. You could also try a data structure for general polynumbers, for polynomials, and then but that's a bit of a that's maybe not easy. Super not obvious approach, which Wildberger talks about, and I want to talk about and add to WFC net. I also want to make a scripting engine so that you can run scripts, but that'll take a while. I was gonna put this. I wrote a revelation about how to use there's these parsing tools called LAIX and YEK in Erlang, and I was gonna maybe rewrite WFC parser. Oh, I wanted to talk about how because that was a thing I added, was a new string parser. That's something I want to talk about. But I wanted to, lost my train of thought. Doesn't matter. It's right there. It's not quite lost. It's right there in the distance, though. I don't know, I probably said I wanted to talk about the Mobius transform. I wrote a Revelations 20, about parsing, and then I discovered that those tools are really just not good enough for what I want to do. What LAIX is good, but YEK is not up to what I needed to do. Verding wrote one called something that's similar to YEK, which uses a different theory of parsers called spell one. The problem with YEK is it doesn't seem like it has a way to accept partial input. So if it's this multi-line problem is really the one I want to solve. So IOR of 1,1, it should recognize that I'm halfway through parsing that because there's no closed paren. I should also add rainbow parens. That would be cool. IOR 1,1, and then give me the opportunity to continue my line, but oh well. Yeah, now Bool Mobius transform is really cool. It's its own inverse. It's really like, what the hell. I am going to probably talk about complex analysis and fractals, and the Mobius transform is really important in complex analysis, so I don't think there's a good long YouTube playlist on complex analysis, so maybe that's right up my alley, is talking about things that other people haven't talked about. I don't like analysis very much. I used to love it, and then I've started watching Wildberger a lot because I'm programming, and he writes the math in a way that is really, so if I write a program to do X, I will go look at Wildberger for how to do X, because he will formulate it in a way that's easy to convert into a computer program. And what I've realized is analysis cannot be converted into computer programs, and on some level I already knew that, but then I realized that, oh, this represents sort of a fundamental flaw in analysis, and then there's this question, oh my god, there's so much cool analysis, and it seems like, anyway. Yeah, so this is called the Lying Knights problem, or I don't know what it's called. But basically, talked about this in the podcast. There's this really complicated riddle that you can write as logic, and then the question is, you take the conjunction, you take the negation of each of these because each knight is a liar, then take the conjunction or the and of all three, and then ask, does that conjunction imply gold, marble, or stone? And it's almost impossible, even solving it by hand algebraically is kind of, in WF algebra, is really difficult. In Boolean algebra, it's pretty much impossible. You could maybe write out truth tables, but man, that's a lot of grunt work, whereas in WF algebra, one of those reduces to 1 and the others don't, which is cool. And we went over that in the podcast, and I think it's still in the WFC codebase. Okay, I think that's all I wanted to talk about. What were the exercises? Yeah, write out by hand how to derive. I think I did that. Print out its intermediate steps. That would be nice. So there's no way to get around the reduction right now. So then maybe that would be nice. I deleted code that does it. I need to go and edit this. I need to edit this. Oh well. I think that's all for this video. I was surprised how much of that I got through. You know what? You know, I want to go through next. Here, this is what I'm going to do in the next video. The only changes I've made to WFC, I think, I might have to look at the Git history, but the only new thing is this string parser, which is what, you know, if I type Google Gobble, it sends it to, I think, read-eval format, or no, it's read-eval format safe. Right, it sends it to this, and then it's either OK result, in which case the result is pretty formatted, prints it, or error, in which case it prints an error. So that's how it works. In fact, here, let me just show you. So and it'll, right, but if I do this, yeah, error read invalid value, here it's the same error. Or if I do error, where is it? No match of right hand side. Error bad match. Okay, Google. That's interesting. I don't know how that works, but we'll have to see. So maybe the next video will